I'll try to keep my talk brief and leave room for questions for you. So why I'm talking, I'm not a cybersecurity expert for the first, so I don't know much about the actual cybersecurity attacks, but I know a lot about programming. And in our work in Software Center, what we focus on is we focused on improving the technology that is available for programmers. And one of these areas that we work with recently is the cybersecurity. So looking at the patterns of secure programming, secure design, looking at the anti-patterns, looking at the known common vulnerabilities, and try to extract information that would be useful for a programmer or architect to improve their product based on that, and do it in a more automated way. So we do this with this cool thing that has been around for a while now, but I don't know if you have heard about GitHub Copilot. Most of you probably have. So the technology behind GitHub Copilot is the Elon Musk's OpenAI and CodeX model, which is a huge language model that can do a lot of things. It can help in how to program, but among other things, it can also help to quantify programs, functions, lines of code into embedding vectors in neural networks, which can help us to do things like comparing programs more of on a semantical level, not really semantical, but contextual level. So it's actually really cool because this kind of language models, they have gained their popularity in recent years because of two things. One was because they're actually very, very good in understanding natural language. So Google's translation was one of the first applications of those big language models like BERT. Now, that's one thing. But the other thing that they're really good at is that they actually manage to understand the concepts of language, both programming language and natural language, on a bit higher level. So the idea of, for example, translation between two languages, natural languages, is based on the idea that similar concepts would be placed in a similar area of the neural network or the embedding vectors. And that's even true for programming languages. And the other part that makes those models really powerful is that they're essentially models that could be pre-trained. So you don't have to train those models, or we don't have to train those models from the very beginning. They already come pre-trained with either a base understanding of an English language or any other language, or even a base understanding of a programming language per se. So what we could do is we could take a language that has been pre-trained, and those languages are really huge. They, for example, the CodeX model that has 175 billion parameters, which is really, really huge. That's about 100 times bigger than any other language model that was developed previously. So it requires huge amounts of both energy and processing power to train those models. But we can use that by basically taking the base model and then adding few more epochs to train that model on our specific tags, or even build upon those models in a very smart way. So the reason why we can build on those models is that they actually work in a smart way with all kinds of natural language related tasks. So when we see a task, for example, a sentence like change this to a static instead, which could be a review comment from a review database, could be a program of some sort, we see it as a word. But as neural networks that work on natural language processing, they see those as vectors of similarity between words or sentences to other sentences. And these similarities actually have meaning. So they have meaning in two ways. One is that they quantify each of those words, and we could plot them on a multidimensional space. Here is an example of how I plotted them just by taking those numbers that are on the screen. They're of course not really representative. I mean, real models would provide somewhere between 1,000 to 4,000 numbers in these vectors. So those are really huge vectors. But if we just simplify that to two numbers and try to plot them somewhere on those spaces, then we could quickly see that there is some logic to this chaos. For example, if you look at the word static in this, those are words like any other words, but if you know C and C++ and even Java probably, then you know that those are also keywords in programming languages, right? So if you look at all the other words, they're somehow related a bit close to one another, much closer to than anything else, right? And then we have a word change and instead and to, and the words instead and to, not that often used in programming, I would say. Maybe they could, the word to could be part of a function name or a variable name, but most likely they will not pop up there. So that's one property of those embeddings. The other property is that those vectors having a meaning, and they allow us to make arithmetical operations on them. So both calculating a distance between vectors is meaningful in that space, and also calculating things like adding or removing vectors also makes a lot of sense. And this is the basic of how we use those models in our research. So what we basically do is that we take those models and do the embed programs in these models, both the reference programs and the programs that we want to study. And then we try to understand how far they are from one another. So we could do things like, for instance, add in different words or different programs and try to look for what the program would be, try to look for programs that are similar to one another. And if we just focus on the similarity, that similarity in the context of programming and cybersecurity is the key to what we are working with. Because what we actually do is that we, in the essence, we take a pattern, secure programming pattern, for example, a secure logger, as I will show you in a moment. We do some manipulations of that, and then we can use that pattern to find similar code to that particular pattern. And then depending on how much modification we introduce to the pattern itself, how much extra code we could inject into that pattern, we get closer or farther distance from that pattern. And by doing that, we could calculate how secure or insecure those different components of that product are. And of course, that looks fantastic. But if we look at reality, I mean, this is how it's not even a huge code base. That's a code base of about 10,000 lines of code. If we do it by line, you see there's a lot of patterns over there, but there's a lot of dots, right? And each of those dots is essentially one vector of about 4,000 elements in that. So finding similarity is not as simple as one would think, because those dots that I marked over there, there is a green dot in the middle, and there are orange dots all over the place. They are essentially the closest dots to one another, even though if they are not seen over here, right? That's simply because the transformation from those 4,000 dimensional space to 2-dimensional space cannot preserve all the properties, right? There's always something that's get lost. But if we just focus on distances and just focus on cybersecure patterns, we did some very simple experiments with the secure logger pattern. So secure logger pattern is a pattern that says that every information that one stores in a log file should somehow be encrypted. And if you look at, for example, log files from Windows machines or Mac machines, you will see that all data is basically open text. And that's maybe not a problem if we have our computer for ourselves, but if we are sharing the data somewhere else, that becomes a problem, because those log files usually contain things like usernames, IP addresses, DNS addresses, could be all kinds of very important information for the designers and for the maintainers of the systems and operators. But if they are all in open space, then you could directly see that conducting an attack having this kind of information about your system is really, really easy. So secure logger basically says that you should encrypt everything. So in our work, in this simple example, say that we have the reference implementation. That's actually implementation from the Carnegie Mellon University's report. It's not something I create myself. That's their example implementation. And there you see that there is some sort of encryption happening over there. So what happens if we take two other examples? So say this is our reference implementation, the core of the example. We're going to look for programs that are similar or not similar to this kind of implementation. Now I'm just looking at giving you two examples of two modified programs. One program on the left has basically that part removed. So there is no encryption, just normal text. We could do even more modifications if you wanted to. And then the other program that has a very minor modification, basically a different sign over here, just as an example. And if we do the magic with neural networks, if we calculate the embeddings, then the embeddings would look something like at the top of the screen. So very, very long vectors of a huge amount of numbers that nobody really understands. If we plot them on two-dimensional space, here I'm using a PCA, principal component analysis, then we would see that the secure logger reference, that the first program, the unmodified program, is over here. And then we have a insecure logger and then a secure logger somewhere there. Now the numbers in PCA don't really mean much, so the axes don't matter. But if you look at the distances themselves, we could see that the distance between a secure logger implementation and the reference implementation is actually smaller than the distance between the secure implementation and insecure implementation, so to say, right? So by doing this kind of distance calculations, we could do, and using all kinds of modifications, we can find places in the code that violate certain security design patterns. Now, in this particular example, of course, it's even possible to do it by textual searches, but in a more complex space, when we have a bit more complex design patterns, it's not really possible because the patterns are, per definition, something that is on a higher design level. So they may not necessarily even be in the code per se. They may just be types of implementations that we want to do. And those language models allow us to find those kind of implementations in there. Now, the really interesting part of that is that if we actually look at because the biggest challenge when I talk to companies in this area is the fact that we need to have a lot of examples to actually and guidelines how to do that. I mean, how do I do it in my particular product? Which patterns are important or not? So if we look at the secure design patterns from Carnegie Mellon University, they have 5 different, I would say, areas of those. And as you see, only few of those patterns, they actually have some sort of reference implementation. That's both a good and bad. It's good because it gets us somewhere to start with our work, but also not extremely good because those implementations are extremely generic. So we have to use code injections from other products in order to make it even more applicable. And what we also do is that we also search for code that's given either as an example or as a code to test your product against specific vulnerability that have been discovered. And by doing that, we could also find out whether a product is to some extent vulnerable to that particular vulnerability in that particular product, in that particular area. And then you see the data set becomes a bit larger. So I think there were like about 250,000 of those, and 25,000 contain some sort of GitHub examples, both with either as a test or as an example of that CVE in the product. And how we do it is that we take the CVE example, which is a very specific, usually very specific to either a particular product or particular vulnerability. It could be about a particular protocol. And then we identify what is basically that vulnerability about, extract the smallest code snippet that is relevant for that vulnerability, whether that is a specific encryption key, whether that is about input validation. We create a bit more generic example, and then we mix that example with a product code in order to make the model understand the domain of the program a bit better than that. So it will try to somehow lean towards the places in the program which could be relevant, just because we mix that that area of code from that particular programs. And if we do that, we actually did a few studies. So we did a study on Android security defects, because Android has quite a big database of both CVEs and the code is open source. And there we actually found few of those, but we were looking for something extremely specific. I mean, in that particular study, we focused on the particular line that could be problematic. We tested that on a line level. And then we, of course, found that it's possible, but it's not really efficient on a line level, because lines could be embedded in some other parts of the code that don't really make sense for that security vulnerability. And then, of course, the manual curation of data is needed. So then what we did is that we tried to use even more vulnerabilities like this routine reference. And then we checked the products that are relevant for some of our industrial partners that are already open source, but they're being used over there, and try to identify where in those protocols we could observe those kind of vulnerabilities by using that approach. I don't have a slide on the numbers of that, but it seems that we found a few places over there. And then for what are our basically plans for doing this in Software Center in the next year? So basically, we want to continue working with those open source products, try to find vulnerabilities. Then we're going to visit a few of those companies that are collaborating with us in this project, and then try to apply that on their product and see if the product that they have actually developed or modified based on the open source code has better security or lower security based on that. And I think that will stay here. If you have any questions, I will be super happy to answer. Thank you.
Where do you see the main difference are code analysis tools?
So the big difference is that SonarQube and majority of those tools, they look at maybe things like which libraries you use, whether you use libraries that have known vulnerabilities and so on, but they are not able to trace higher level concepts like design patterns or abstract vulnerabilities that require some sort of translation between what's written in the description and what you have in your product code.
So basically, you're trying to connect requirements documents to,
Maybe not requirements documents, but secure coding guidelines documents. Thank you.
I was wondering if you, at Black Hat a few weeks ago, there was a presentation about, I would say, the dual of your research with people showing how copilots can actually introduce vulnerabilities in the software, in the code they are suggesting, and which is not really probably surprising. I think basically anyone that is working in security or software engineering, when they proposed Copilot, we all thought the same thing. But the people had some examples and some quantification of that. I was wondering if you had looked into that research and if you had any thoughts about this, about the fact that if we use software generators, we will end up introducing way more vulnerabilities in the end code.
No, I actually haven't looked into vulnerabilities. I mean, when it comes to GitHub Copilot, we are looking at specifically aspects of the legal aspects of who actually owns the code, if GitHub Copilot helps you. And if GitHub Copilot suggests the code that is somewhere already in the Git with a, for example, copyleft license. Right. But I haven't looked at the vulnerability there.
It's an interesting area.
But I think that I'm not surprised, because GitHub Copilot is a fantastic tool. It's 10 times better than anything else, but it's not perfect. It sometimes suggests very bad code. Thanks. Okay.
I don't know if more, but the problem is that it is trained on a code base that contains the gazillions of vulnerabilities. It's basically the same effect that you have if people like copy code from blog posts or anything else and introduced it. A lot of that code is wrong. So the result is that you introduce vulnerabilities without even knowing about it.
The finish line there is very, very. No.
Well, I don't feel insulted. Thank you very much for having me.